There are many physical quantities that are part of our daily lives. In fact, these quantities can be divided into two types. If it is a quantity with only magnitude, like energy, time, or mass, then it is a scalar quantity. On the other hand, if it is a quantity with both magnitude and direction, such as velocity, force, or acceleration, it is a vector quantity. Our main focus today will be on the latter, vectors. Traditionally, this is what a vector looks like. Vectors are represented using arrows, also known as directed line segments. The length of the arrow represents the vector's size or magnitude, and its direction represents the vector's direction. The initial point of a vector is known as the tail. The end point is known as the head. However, this is not the only way to represent a vector. They can also be represented using algebra. It all started when one day, famous French mathematician and philosopher René Descartes was inspired by a fly roaming around the ceiling in his room. After watching the fly for a long time, he came to the realization that the position of the fly could be described in terms of its distance to the walls of the room. This revelation gave birth to an invention that earned Descartes the title of the father of modern mathematics, the Cartesian coordinate system. Also known as the xy plane, the system is characterized by two perpendicular axes, known as the x-axis and the y-axis, hence the name xy plane. Any point in the two-dimensional plane can be described in terms of its distance to the two respective axes, which is known as the point's coordinates. With the introduction of this system, the field of mathematics underwent a great paradigm shift. Geometry and algebra were no longer two separate entities, but one single whole. Geometry had become a subset of algebra, meaning that anything in the former can be described in terms of the latter. Naturally, this includes vectors, which is what this video is about. Representing vectors with algebra.
But how exactly is it done? Well, to use geometric vectors from abstract space in algebra, the vector can be placed in a Cartesian xy plane. To simplify calculations, the vector tail is placed at 0, 0 at the origin. A vector like this from the origin is called a position vector. Then, the coordinates of the vector head is used. The vector can be denoted in algebraic terms in terms of an x value and y value. In between a set of square brackets, this is known as a Cartesian vector. Note that the square brackets are important, as round brackets are used to denote coordinates rather than a vectors. As such, any geometric vector can be turned into a Cartesian vector in this fashion. One cool thing about Cartesian vectors is that computer can work with them. A computer wouldn't be able to understand a geometric vector in abstract space because it requires exact information on what a vector is. Anyway, a vector has a magnitude and a direction. How can these quantities be formed a Cartesian vector like this? Firstly, a vector magnitude can be found using a Pythagorean theorem. Using a position vector as the hypotenuse, a right-angled triangle can be formed. The hypotenuse squared will be equal to the sum of the square of the both sides. Hence, the magnitude will be the square root of the x value squared plus the y value squared. Secondly, the vector direction can be calculated by using trigonometry. We can find the measure of an angle data using the trigonometric function of the tangent, where theta will be equal to the arctangent of the opposite side over the adjacent side, which is in this case 4/3. Using this calculated angle, the direction of the vector can then be determined. Now that we have established what a Cartesian vector is, let's move on to comparing vector operations which are done geometrically versus that of those done algebraically. Starting off with geometric vectors, one of the most basic operations is a vector addition. Let's say we have two vectors, vector A and vector B. To find the sum of the resultant of these two vectors, we can call this R. We connect vectors B tail to vector A's head, which is the head to tail method. The resultant vector will be this, a vector connecting vectors A's tail to vector B's head. In contrast, the vector addition of the Cartesian vector is easier. There is no need to draw a diagram. To find the resultant vector, the respective resolved horizontal components are summed up. Then, the resolved vertical components of the two vectors are summed up. What this means is that to find the resultant vector, the x values of the two vectors are summed, and the y values of the two vectors are added. The resultant vector will simply be this. Besides vector addition, other vector calculation using algebraic Cartesian vectors are also easier to understand. For instance, vector subtraction of A minus B will simply be vector B 1, 2, subtracted from vector A 3, 4, producing vector R 2, 2. Once again, there is also no need to draw a diagram to perform calculations. In fact, this is true for pretty much all over vector calculation with Cartesian vectors. Scalar multiplication, for example, is just any real number s, which is a scalar quantity multiplied by any vector. Let's say we multiply vector a by -3, we would get -9, -12. In short, algebraic vectors are better than geometric vectors in these three ways. 1. You don't need to draw a diagram to perform calculations. 2. They tend to be easier to understand. And 3. Computers can work with them. Representing vectors with algebra is powerful indeed.
However, that's not the end of the story, because it doesn't just end with the second dimension. Following a natural progression of thought, one finds that if the xy plane is a 2D plane, then adding a third z-axis to the mix will turn the plane into space, a three-dimensional space. A vector in this 3D space would have 3 coordinates instead of 2, x, y, z. Interestingly enough, this doesn't change much to algebraic vector calculations. For example, vector p123 can be added with vector q456. Summing each of the 3 coordinate values up, we would get resultant vector r579. It isn't that much of a bother to perform this calculation or any other algebraic vector calculation. In fact, the z coordinate will just have to be included. As such, algebraic vectors are powerful, as they can even be used to perform calculations in 3 space. The possibilities are endless.